thank you for coming out. This is an amazing turnout. Wasn't expecting this. So welcome to an evening of talking about and introducing antimatter. So I'm a PhD student here. I'm in my second year. I'm a particle physicist. I work at the Bell 2 experiment, which is based in Japan, but I just spend most of my time coding over in my office, like 2 levels above. This talk is meant to be very introductory. So if you have any questions, please do put up your hand. Like, ask me what I'm talking about if you don't understand it. And hopefully it's going to be clear to you by the end of this what antimatter is, why it matters, and what it means to what it shows about the way the universe is today. So a quick outline of my talk, just to show you the roadmap of what we're going to do. I'll try and explain to you what antimatter is. What do I actually mean by the word antimatter? Then I'll look at how it's created, produced, or destroyed. Whether it's created in natural processes, whether we can make it ourselves, etc. And then I'll talk about why there is only matter existent, right? So everything around us is made of matter. So why is it made of matter? So everything from galaxies to the sun to me to you to this chair, it's all made of matter, but why? We'll look at something called CP violation, which sounds a little bit scary, but we'll go into that later in the talk. And then how do we detect that? So how do particle physicists like myself actually figure out these things and look into the physics behind it? So, without further ado. So what is antimatter? Before we define that, maybe we should define what matter is first, right? So matter is made of fundamentally electrons and quarks. The majority is. There are lots of other different types of particles which are much rarer, such as muons, tauons, neutrinos, but we won't really focus on those this evening. That is what matter is, electrons and quarks, which are tiny, tiny particles which clump together and create all the particles that we know today, such as hydrogen, your water, your petrol, everything. I noticed I only said liquids there, but all solids as well, everything like that. So from that, we have matter. What is antimatter? So when we look at antimatter, we only have one slight difference between matter and antimatter, which is that particles have charge, right? So particles such as electrons have have negative charge, most particles have a charge of some kind, positive, negative, or neutral. Electrons have negative charge, and an antimatter particle has the opposite charge to that. So if, for example, we have an electron, we have a negative charge, the antiparticle of an electron will be a positron, so a positively charged electron. There are also other factors, other interesting properties of particles that are opposite or different to a matter particle, but that's a bit more advanced. You don't really need to focus on that this evening. We'll just look at charge. We have particles that are positive and neutral, positive and negative, and we can easily think of that as, the opposite of positive and the opposite of negative. But how can we think of the opposite of a neutral particle, right? So, for example, photons have no charge, but what is the opposite of no charge? The way we can think of this is that you can have a negative 0, and a negative 0 is exactly the same as a 0, right? So if you have a photon, you can have an antiphoton, which is exactly the same as a photon. So a photon can be its own antiparticle, right? Did I explain that okay? Cool, okay. So, from that, what actually produces antimatter. So we have antimatter about us today that we don't even notice. For example, so there's natural and then there's human processes that can create antimatter. So for example, lightning strikes. What happens is, well, lightning is made of electricity, right? Electricity is made of electrons, and these electrons are really, really, really accelerated to really high speeds and energies, and they smash through our atmosphere at these crazy energies and hit our atmosphere as they go through. So these particles hit, as they hit them, they have nuclear reactions, and these nuclear reactions produce something called a gamma ray. Now this is actually just a really, really high energy photon. And these gamma rays can then split in something called pair production. So it kind of looks like this diagram. And these photons basically split into an electron and a positron. So that's our antimatter. Our positron is produced in that. So antimatter, naturally. Then we have beta decays. So beta decays occur in natural processes, and we can also make them occur. And what that is an unstable center of an atom, so a nuclei. It's unstable, so it wants to change itself to become more stable. And so inside this nuclei you have protons and neutrons. And a proton is positively charged and a neutron is not. It's neutral. And so this proton changes into a neutron, and through that it has to conserve certain things, and it gives off a positron. So through that, our positron, antimatter. Nice. Okay, then we have particle accelerators. Now particle accelerators, obviously human-made, and this is where we, kind of like lightning, we really accelerate these electrons or other particles into really, really high speeds and then collide them with other particles, either fixed or also accelerated particles. So we get incredible, incredible energies. And again, we can produce many different types of antimatter in that way. And then finally, something called cosmic rays. Cosmic rays is a little bit of a misnomer. It's more of a particle, a really high energy particle, coming in from outer space. And what this particle does is also kind of like lightning. It comes in at a really high energy, hits our atmosphere, and as it hits our atmosphere, it creates something called an electromagnetic shower. Now what that is like a shower of tons and tons of particles created by, again, gamma rays through these interactions. And these gamma rays split through this thing called the pair production and creates the positron and the electron. So again, antimatter. I will just say that antimatter doesn't have to be a positron. I know I keep using that word, but positrons is just a really good example and will come up a lot. But you can have anti-hydrogen, you can have anything you want. Yeah, okay, so we've said like what creates antimatter, but what actually destroys it? It turns out pretty much everything. So, because, okay, I'll just go to the next slide. So, oh, if it works. Yes.
Okay.
There we go. Where was I? Antimatter destroyed. So, annihilation is what happens when antimatter meets matter, right? So, as soon as antimatter and matter touch, they annihilate completely. They give off a ton of energy, and it's kind of like the opposite of pair production that I was saying. Like the gamma or the photon turns into an electron and positron. It's kind of the other way around. The electron and positron come together, touch, and give off gamma rays. They give off the energy, or photons. So because of this, because of this, it's really hard to make things out of antimatter, right? Because as soon as you create it, it's going to be destroyed by all this matter that we've got around us right now. But it has actually been done. You're able to suspend antimatter, in a vacuum. So a vacuum is an area that doesn't have any particles in it. We've sucked all the particles out, so there's no matter there for the antimatter to annihilate with. And there's an experiment at CERN called ALPHA, and they managed to suspend some antihydrogen in their experiment for about 1,000 seconds, which is quite record-breaking and an amazing feat, even though it doesn't sound much. 1,000 seconds, what's that? 10 minutes, nothing. But it's an amazing feat, and it's allowed us to look into more properties of antimatter because we don't actually know much about it. Okay, so why is there only matter, right? So why are we only surrounded by matter? Why are we not surrounded by antimatter? Why are we not surrounded by both? So to answer that question, we kind of have to look at the laws of physics, right? So in general, the laws of physics are very symmetrical. There's lots of physicists like symmetry, and it turns out like laws of nature, they like it too. And so somehow in the progression of the universe, the matter somehow won out over antimatter. Somehow there was slightly more matter produced than antimatter. But because of these laws of symmetry, you'd expect that matter and antimatter would be produced equally, right? So does that mean the laws of physics are different from for matter and antimatter? Does that mean like somehow there's some asymmetry, some kind of non-symmetry between them? So are these symmetries of physics broken? So if we look back at the beginning, back at the just after the Big Bang, so just before the Big Bang, everything was condensed into an incomprehensible something where everything was stored, and then the Big Bang happened, everything expanded really, really fast, and in the first trillionth of a second, everything expanded to a massive, but actually really small, but relatively massive, 1 times 10 to the minus 33 centimeters, which is 0.33 zeros, and then a 1 centimeters. So that's really, really, really tiny, right? And so the whole of the universe was compressed into this tiny space. So it was super compressed, super dense, really, really hot. And, 1 times 10 to the 32 degrees hot. Doesn't matter whether it's Kelvin or Celsius at this point, or Fahrenheit. It's just really, really hot. And just after this point, actually, before that, the matter and energy, everything was pretty much like a soup. It wasn't really distinguishable. We can't really separate the things. They're all the same. And then just after this, as it starts to expand, things start to separate. They become their own things, and so energy and matter become separate entities, and we start getting particles and things. So this. There's a process just after this called baryogenesis or baryogenesis. I change my pronunciation every time. That caused this matter-antimatter asymmetry. So there was a process that actually changed the fact that we expect there to be a symmetry. It changed the production rate of matter and antimatter. So for baryogenesis, we have some conditions. So in 1967, this guy, Andrei Sakharov, I think I pronounced that correctly, he said that there's 3 things that we need for this, for the matter-antimatter asymmetry. So the first 2 we're going to kind of ignore. Baryon number violation, interactions out of thermal equilibrium. Basically, if they don't happen, then the antimatter-matter symmetry would have been fine. But we're going to focus on this CP violation because this is where my experiment comes in. So I have a little bit of a bias towards it. So CP violation, what do I mean by that? That's completely just alien, even to me most of the time. So to talk about CP violation, I haven't even said what the CMP is yet. we need to talk about symmetries that I was talking about, the laws of physics. So in these symmetrical laws, we have the charge, parity, and time symmetry, so C, P, and T. So the charge symmetry looks at the charge of a particle, and if you put this, you take the symmetry and you put it on the particle. So you have an electron, and you transform, I guess, this. You put the symmetry on the particle, and it changes it to the antiparticle. So it changes the sign of the charge, right? So if you put this symmetry on an electron, you get a positron. Now, then we have the parity. The parity symmetry is kind of like inverting spatial coordinates. And by that, I mean, if I'm standing 2 meters away from this wall, and I invert my coordinates, I am on the other side of the wall at -2. Then we have the time symmetries, and that would be having, like, reversing time, so kind of rewinding and seeing exactly the same thing in physics. So it was, when these symmetries were thought up, they were thought to be symmetry, but there is there are actually violations to these symmetries, like each individually, so they combine them, and it's like, oh, well, we can't have the combined ones, they have to be symmetrical, they can't be violated, and it turns out they actually can. And so this is where this CP violation comes in, that's what I've been talking about. So they combine this charge and parity symmetry and see if it gets violated in any interactions in the laws of physics. And yeah, so an example of this symmetry would be an electron traveling left. Is this your left? Yeah. Electron traveling left, and then I'm applying your CPT symmetry or transformation, and then you would be a positron traveling right. So, yeah, cool. I think that's all I wanted to say. So, a quick history of charge parity violation. So it's been discovered. We've seen it. There is violation in this law. And in 1964, this guy, these guys, Cronin and Fitch, they found that CP violation existed in something called a kaon decay. A kaon is another type of rare particle. And in 1980, they were awarded the Physics Nobel Prize for it. Woohoo! And yeah. Then in 1999, Bell and Babar, which are particle physics experiments, they observed CP violation in a different type of particle called a B meson particle. So this has also been observed. And then in 2008, these three men here, I can't remember his first name, Nambu Kobayashi and Maskara, they won the 2008 Nobel Prize in Physics for their prediction of the third family of quarks. And this was essential for CP violation, like the explanation of it. So that's a quick history. So, oh, not again. CP violation. So, CP violation was discovered. We've seen it. We've got some evidence. It exists, and we see astronomers predicted that at the beginning of the universe there was about 1 quark in 100 million left over from 1 quark in 100 million was left over from the Big Bang. So 100 million were produced, and then they were annihilated almost instantly, and we have our 1 quark left. So if we look at that in terms of kind of like the human race, that would be, so of the 7 billion-ish people that exist, like if everyone touched each other and annihilated, then that would be about 70 people left. So yeah, not many. So what actually happens when we look at our CP violation experimentally, from our evidence, what we've seen, is that the amount of matter in the universe predicted falls short of what has been observed, right? So we're predicting CP violation does this to matter, but actually we've noticed that there's a lot more matter than that. So we're wrong somewhere. So in particle physics, we have something called the standard model, which it kind of encompasses all of what we try and model the universe in the way it is. And so from this experimental evidence, we think that the standard model might be incomplete, and other sources of this CP violation must exist. So this is where the experimentalists come in again and go, okay, like where can we find this? These are extra sources. So this is my little demonstration of an accelerator. You probably can't see it, sadly, but I also put it on the slide so that we can see it. Basically, we accelerate particles together as an experimentalist. We accelerate these particles, we smash them together, and we see what comes out. But how do we accelerate them to do this? And what we do is we have a huge source of energy, normally the grid or something like that. This is my little Van de Graaff generator. And what we do is we, this is not ideal. We oscillate an electric field to accelerate these particles as they go. So I'll just turn this on and get it. Oh, I forgot to plug it in. That's always a good start.
Can you use the table over there?
If it, I mean, if I put it on the table, then the view still isn't very good into the bowl. So I'll put it on, and maybe a few of you could stand up or whatever.
You can leave it on and have people look at it on the way out.
Yeah, okay, I'll turn it on at the end as well. So I'm charging up my accelerator, and then I insert my particle into this accelerator, and hopefully it should spin around, kind of. It looks like it's affecting the thing. Or okay, well. So what should be happening, and isn't really, is that the ball accelerates around and around and gets faster and faster. Now, things like friction come into effect here and slow it down and stop it from reaching a really fast speed. I wish I could get it to go to the speed of light, but I don't think that's physically possible. But this is the idea of a particle accelerator. Now, it is a little bit different. Particle accelerators tend to be a little bit bigger. For example, the NHC, which is going over a few different countries' borders. I'll just turn this off. So, I'll just, I could play it again, I guess. So, this is kind of obviously an analogy. And what happens is, the difference between this and a particle accelerator is that the particles we accelerate tend to already have a charge. So, instead of, like here I give the little ball a bit of charge, and this charge oscillates between positive and negative each time it touches a metal strip. But in a real particle accelerator, we tend to have electrically charged particles already. So what we do is we oscillate the electric field at a really, really fast rate, and have bunches of thousands and thousands of particles going through every second. With this oscillating field, and the oscillating field is what accelerates these particles to speeds close to the speed of light. So they have huge energy, and then we smash them into things, and then we see what comes out. Also, the bowl kind of represents the circular motion that we tend to go for as particle physicists, because if you think about it, if you have a circle, you can keep accelerating and keep going, and it gets faster and faster and faster, whereas linear accelerators, even though they do exist and they are often used, they have just one length, and you have to accelerate it in that length, and it's a lot more difficult to get up to these really, really high speeds. So that's why a circular accelerator is much better. And how do we make it circular? Because like normally when you accelerate something, you have to put it in a straight line, right? And we can't just nudge it to go around the circle. Like if it touches the walls of the accelerator, then it's going to annihilate or interact with the accelerator walls, right? So what we do is we suspend these particles in a magnetic field, and these magnetic fields are huge. We use superconducting magnets, and they way more powerful than like anything you've probably come into contact with. And these particles, because they're charged, the way a particle interacts with a magnetic field is that it starts to bend. So we use these magnets to bend the particles around these circles. So it takes a huge amount of power. It's crazy. So yeah, that's a particle accelerator. So once these particles smash into something, how do we see what comes out? This is where particle detectors come in, and which is what I work on. I work on a particle detector. So how do they work? They can work in different ways. A lot of particle detectors kind of sit there. They're not connected to an accelerator, and they look at particles coming in from outer space, or whatever you could look at. I don't know, maybe close to a nuclear power plant. But my one in particular is connected to an accelerator, and what they do is they have different components and different components to look at different types of particles. So back in the day, when they were first developing this field, one of the first types of particle detector was something called a bubble chamber. And what happened is, as a particle comes in, it would interact with a liquid that was just under boiling point, and would ionize this liquid. And that means it rips away all the electrons attached to all the atoms and creates little bubbles in the track of the particle. And then we take a picture of that particle. So here, I don't have a laser, here you can see something comes in here that we can't see because it doesn't interact with the bubbles. And then we have, coming out to the left and spinning, we have an electron, and coming out to the right, we have a positron. Now the reason they're spinning is because they're in an electric field, right? Like I was saying, the particles, because they have a charge, they curl, they bend. So that's why these particles have curled out into a thing. If you didn't have an electric field, they'd just split and go in a straight line. So yeah, we have our matter and our antimatter. Next, as you may have seen outside, is another early type of detector, which is the spark chamber. Kind of works in a similar way to the bubble chamber, in that a particle comes in and interacts and ionizes with the helium that we've used, but you can also use neon or other gases. But we use the helium, and the ionization allows for a spark to follow where the particle track has gone. So after the talk, it might be running again, so check that out if you didn't get the chance to. Yeah, pretty cool. And usually those ones are muons. Oh, again. Okay, so for a more modern particle detector, we use a lot more advanced technology, not bubbles or sparks as such. But we also have for different types of particles, we have to look at different things to be able to identify them. So here, this is a picture of an atlas detector, and we have different segments to detect different types of particles, right? So for example, here we have an electron coming in, and this electron doesn't get detected by the beginning, but gets detected at this electromagnetic calorimeter, which basically means detect the energy of this electron. And for other particles, for example, the neutron is negatively charged, so it's hard to note, it's hard to see until you get to or you wouldn't see it until you got to this section of the detector, where you detect something else. There's also particles that don't interact with anything. So you may have heard of the neutrinos, which have no charge at all. Really, really hard to detect. They have been detected though. And yeah, these pretty much go through completely our detector. We don't even notice they're there. We have to figure out whether they were there using mathematics and the knowledge of the other particles that happen in a decay. We also have, for example, a muon. A muon was the particle that you were seeing coming on the spark chamber. They are really energetic, so they often just pass straight out of the detector completely. So yeah, that's a modern particle detector. So I'm going to talk about my one now, because it's very close to my heart. So we have, in Japan, we have a detector and an accelerator. The accelerator is called Super Keck B, and the detector, the accelerator is Super Keck B, the detector is Bell 2. I work on Bell 2. So back from the history of CP violation, I said that kaons were the first particles that showed the CP violation. But it turns out that they're very difficult objects to model in theory and such. So people moved on to B mesons, which is another type of particle. And they are a lot easier and ideal almost for measurements of the CP violation that we're looking for. So that's Bell 2. This is roughly where it is in Japan, near Tsukuba, if anyone knows that. So Super Keck B, the accelerator, it accelerates electrons and positrons and smashes them together at such an energy that the B mesons are created pretty much all of the time. And then we look at the decays of these B mesons. We look at we look at the properties of all the different types of decays. It decays into hundreds of different channels, different possibilities. And then we look at all of these, we compare them, and then we look for this CP violation in our results. So, yeah, that's the beginning of Super Keck B. So this is what it roughly looks like in cartoon form. So this is where the Bell 2 detector actually is in the ring. The ring's about a 3-kilometer circumference. So it's not as big as LHC, but we don't need that size for our what we want from it. So here we inject our positrons and electrons, and then we insert them. We accelerate them from we accelerate it into here, and then we have these 2 rings going around opposite directions. So that's how we get our get ready for our collision. And then once we've got them up to like speed and energy that we want, we then join the beams and smash them together. And then we do that inside a very precise point in our detector, and then see what comes out using all of those different segments that I just showed you previously. Now, we have something called a luminosity, and we are almost I think we're record-breaking luminosity at Bell 2. And by luminosity, I mean like how many particles we get out when we get all of our data, and it's going to take a couple of years for us to get all of our data. So we get something called 50 inverse attobahns of data, hopefully by about 2025, and that is equal to 100 billion B mesons for us to all study. So that's going to be a lot of work for me in a couple of years. Well, I don't know if I'll be working that long. Super Keck B and Bell 2, we and they will be looking to verify whether CP violation, all of the data that we collect, we'll be looking to see if the standard model of particle physics is consistent with what astronomers have seen, or whether we do need to change it. Something is different. There is new physics that we haven't seen yet. This is a picture of one of our first events. So the Bell 2 detector has only really just started running this year. So this is one of our first events. So woo, yay us! And this is what it looks like inside. There's some little people here to kind of see the scale. So you can kind of, it's not too clear, but you can kind of see these different segments compared to the Atlas detector for our different areas look at things. So yeah. So in summary, antimatter is an opposite particle to the matter particle, and then at the beginning of the universe, matter-antimatter asymmetry, the matter won because of this CP violation, and CP violation is the main contribution to this asymmetry, and that's what we're looking at today. But we're still trying to find out all of the exact reasons and sources and where it's coming from. And as I have time, I had some like scenarios. So what if so we have the vacuum of space, right? So what if galaxies were made of antimatter? So by that, what I mean is, so people generally see that the space between us and other galaxies is a vacuum. There's nothing between us. It turns out it's not actually exactly a vacuum. There's lots of intergalactic dust and stuff. But what if a galaxy was made of antimatter? So if it were, it would be absolutely catastrophic. For example, quite often we see galaxies merge together. So if we had a matter and antimatter galaxy merged together, it's going to be pretty messy, I think. But we don't actually think they exist. And this is because, well, it's possible, but we haven't seen it. Mainly because of what I said about the vacuum of space not being an exact vacuum. There's actually interstellar gas that exists between us and other galaxies. And this interstellar gas would actually be made of matter, right? So these antimatter galaxies would be starting to annihilate with this intergalactic dust, and we'd see these photons being given off by this annihilation, all this energy. We'd see it coming off, and that would be called something. It would be called a gamma ray glow. Now, we haven't seen that, so it's not likely that antimatter galaxies exist. But just because we haven't seen it doesn't mean it doesn't exist, right? Also, what if the universe were made of antimatter? Oh, great. So what if the universe were made of antimatter? So what I mean by that is, what if instead of matter winning at the beginning of the universe, what if antimatter won? So if we just look at the charge that I was talking about, so if that's all we consider, not much would be different. Anti-me would be talking to anti-you about anti-antimatter right now. So yeah, not much difference. But if we look at a little bit more deeply, so I said that at the beginning I said that there were some other things that change when you change between matter and antimatter. And something that changes is something called helicity. Now, neutrinos are particles that don't have any charge. So when you look at an antineutrino, it's going to have the same charge, right? But if we look at this helicity, this other property, that does change. So helicity is kind of like a particle traveling through space and spinning. So a neutrino has a left-handed spin, and an antineutrino has a right-handed spin. So that changes. That becomes opposite. So yeah, if that is considered in this anti-universe, it would actually be quite a different universe. So it was discovered back in the 1950s that the decay rate of differently oriented particles, so the left-handed and right-handed particles, is actually different. And this was actually a proof of this parity, the P violation that I was talking about earlier. This was found in the 1950s. And the universe wouldn't look. I don't think it would look anything like our universe today, because these particles would decay at different rates. We'd have different processes. It would. I have no idea what it would look like in honesty, but it would be different. So yeah, that would be interesting. But case 3 is something I found out about when writing this talk. So earlier I was talking about this alpha experiment where we're still looking at these. We're looking at the properties of antimatter, right? We've only just really started to understand it and been able to hold it for more than 1,000 seconds. So there isn't actually experimental proof hard, like, yes, we know this, and there's no proof whether antimatter has something called antimass, right? So this would mean that it reacts in the opposite way with gravity than normal mass does right now. So it would repel rather than attract with gravity. Yes, you have a question?
Well, photons are their own antiparticles, so I don't think they give.
So, yes.
Photons definitely, light definitely is attracted to gravity, so it's more an antiparticle, and antimatter would be repelled by gravity, and photons would be, so I don't think this could.
Yeah, exactly. Good point. So if you didn't hear that, like, photons are an antiparticle, so photons, how does that work? If gravity repels rather than attracts, then photons, if they're their own antiparticle, how does that really work in the sense that gravity, because photons are bent by large amounts of gravity. So, yeah, the consensus is that answer, that antimatter will interact with matter, will interact with matter with gravity as matter does. So that's what most particle physicists think. Like no one actually thinks that this, or maybe some people do, but yes.
Are they running some experiments at LHC to actually test the anti-gravity of antimatter?
Yes, they are. They are testing it right now. Currently, they do not have a sign on it. What I mean by that is they don't have a. They don't know whether it repels or attracts because they haven't had enough time to look at it because they suspend it. It's quite difficult to see which way it moves with the effect of gravity. So yes, we are looking. People are doing that, but it's not proven yet. And but the consensus, the general consensus is that we don't think it's going to be anti-mass. We don't think that happens. But if things did have anti-mass, then the universe would be pretty boring. Everything would repel. Nothing would clump together. Nothing would make structures, and it would just be an all spread out mass of boring. So yeah, that is the end of my talk. So thank you so much for coming. I hope you enjoyed it. I hope I was clear. And please do come to our talk next month. This is a great opportunity for grad students to come and talk about their passions. And if you have any questions, please ask now or come and talk to me afterwards. Oh, there we have some questions.
You said if another galaxy was made of antimatter,
yeah,
we would know by the gamma ray glow. But other than that, do we think that the light from a galaxy made of antimatter would be different than ours?
So I don't think so. I'm not an expert, but I don't think so because photons are their own antiparticle, right? So they are exactly the same. So what we would see would be photons. They wouldn't be very different, I don't think.
Different color, different spectral range?
I don't know. That's probably more of an astrophysicist. I don't think so, but I honestly don't know. I'm not an expert in that. But that would be really interesting if that could happen. Yeah. Yes, up at the back of there.
Why do CP violations only occur in some processes and not others?
Honestly, I don't really know the answer to that one. But it. No, I'm sorry, I don't know the answer to that.
Alternatively, is there something particular, something common with all of those processes that have CP violations, or are they just what we've found so far that happen to have these violations?
So there are theoretical reasons why, we theoretically worked out that B mesons would be better to look at before we actually started looking at them. So theoretically, yes, we can work out something that is going to be better for CP violation. We can find other decays that will have CP violation, hopefully, or predict that. Yeah. Hi.
I think I missed something. when was it discovered that antimatter exists really?
Oh, so that was back in, I can't remember the,
And
I think,
how did they prove it?
okay, wow. So I think that was back in 1918 when they discovered the antiproton, I think. This is off the top of my head, I cannot remember, but
1928 was in
28, there we go, thank you.
It was predicted before it was discovered. Yeah.
Yes.
And what was the proof, sorry, that it was an antiproton?
Again, I'm sorry, I don't know. But perhaps maybe someone in the audience could answer?
So all hypothetic that antimatter exists and the CP violation is what if the antimatter didn't exist, then that would not, that would contradict the Big Bang theory. Because I don't believe in it, I believe that the universe already existed.
Okay.
And it crashed, and then that was the Big Bang. It's when the universes crashed with each other, and then when everything was thrown out in one direction, and that made the universe. I don't believe that there was almost nothing, and it became all these universes.
Okay, so yeah, completely. The Big Bang is very theoretical, so it's not concrete. It's a very widely accepted theory, and from all of the evidence we do have, it is what we think did happen. But there are other theories. They do exist, and like yours, it is possible. We could entirely be wrong. We don't have a video camera. We can't look back. So I'm not saying it definitely didn't happen.
I have a reason to believe it could be correct because the people who are working on string theory, they don't get the, I don't know what unit it is,
Right.
Go through zero.
Yeah.
And that because zero would mean there is nothing, and because the part that they justified, the parable, shows that the string theory works,
Right.
and suddenly it doesn't work anymore when we get close to zero. So
Yeah.
I think they just should abandon the zero matter and
Yeah.
continue with
Yeah.
the string theory.
Yeah. So
We'll cross the axis
yeah.
on certain number that's bigger than zero.
Yeah, yeah. So yeah, like I said, there are many different theories, and some definitely do that. They ignore the zero.
There are some physicists working on that.
Yes, theoretically, yes. Yeah. Hello. So antimatter and dark matter is they're different particles. Well, we think. We still haven't discovered dark matter, right? So we're still looking for that. We don't know what it could be. We have a lot of theories, but it's so to distinguish between antimatter and dark matter. I would say that antimatter and matter, they are physical particles that we have seen already. They definitely exist. We have experimental evidence for it. Whereas dark matter is, oh wow.
We have no idea what it is.
Yeah, we have no idea what it is.
So like
We-
Hannah talked about, antimatter is sort of like the same particle with a different charge. We don't have any real information about the charge of dark matter.
Mm.
And so dark matter could be one of two things. It's either something that we don't interact with, which in contrast with antimatter, we would annihilate.
Yeah.
And dark matter could just be in this room right now, and we wouldn't know because we're not interacting with it.
Mm-hmm.
Or it could just be real matter, normal matter, that we don't see. And so very massive things in the skies, like black holes or a neutron star, just normal matters that are not emitting any photon, or enough that we can see.
We don't know the names.
Sorry, I'll ask. Yes, in the back.
Wondering,
Yeah, I'm sorry, I missed the end of that. Could you speak up a little bit louder?
So basically, like if you have small mass, if you have small matters and antimatter, how the chemists like how the physicists they're going to like explain the conservation of energy and also conservation of mass in terms of like equilibrium.
So, okay, if you didn't hear that, it's if there is this violation, how do physicists explain this conservation of energy and mass, which we do expect? Is that the question? Yeah. So, okay, so we have violations in our processes, our separate processes, but we don't have a violation in the conservation of energy or mass. So the violations I'm talking about aren't to do with energy or mass at that point. So there is still energy and mass conservation. So I think that is.
We'll take one more question, and then afterwards you can come to talk to Hannah.
Okay. All right. You have that?
Is it true that if you have a particle accelerator that's large enough and powerful enough that it could create a vacuum in the Higgs field and destroy the universe?
Well, so, I mean, theoretically, anything's possible, but pretty much no. Yeah, it would need an infinite amount of energy, and we just don't have that.
All right. On that note, let's give it a round of applause.